All right, let's say that B sub n converges. So it's just some comparison series that I picked, and I know that it converges. Then A sub n will converge if I can prove that A sub n is less than or equal to B sub n. Okay, so what that means is I've got a convergent series. Let's say that series is 4 plus 2 plus 1 plus 1/2 plus 1/4, etc. And I just told you that it converged, but why does that series converge? Right, it's geometric and the R value is less than 1. So it's a convergent geometric. All right, let's take another series. Let's say that series is 4 minus 0.01 plus 2 minus 0.01 plus 1 minus 0.01. Okay, do you see the pattern here? I'm basically taking the original series, or this convergent geometric series, and every single term is just 1/100th less than that series. Is this new series 4 minus 0.01 plus 2 minus 0.01 plus 1 minus 0.01, is it a geometric series? No, it's not geometric. But every single term of the second series is smaller than every single term of that geometric series. So if I continue to add them all up, shouldn't it add up to be something that not only is finite, but is smaller than that geometric series? Okay, so that's what we're talking about right here. If B sub n converges, then A sub n will converge as long as A sub n is smaller. Okay, now the exact opposite happens for a divergent series. If B sub n diverges, then I need to prove that A sub n is bigger than that known divergent, and then it will for sure diverge. The problem would fall if these inequalities are reversed. If you know B sub n converges, and it ends up that A sub n is bigger than B sub n, well, it could just be a little bit bigger and still converge, or it could be a lot bigger and diverge. Yeah, I might not have completely thought this through, but what I was trying to do was create a series on the top of my head that was just a little bit smaller than that given series. Okay, so let's go back to the same problem that we had in number 4 where we couldn't find that limit, and let's see if we can use the direct comparison test. So I'm still going to compare this to 1 over n squared. And we know that that's a convergent p-series. All right, so the limit comparison test didn't work, so I need to prove that my original series, does it need to be smaller or bigger than 1 over n squared? Smaller. If you're trying to prove convergence, your original one has to be smaller. So I'm trying to prove, and you can literally say, okay, sine n over n squared plus 1 needs to be less than or equal to 1 over n squared. That inequality doesn't mean much to me, but if you cross multiply, and whenever you cross multiply across an inequality, make sure that you always go top left to bottom right first. So sine n times n squared less than or equal to n squared plus 1. Now, if I were to ignore that sine n, would you agree that n squared will always be less than or equal to n squared plus 1? Okay, absolutely. Sine n, remember, fluctuates between -1 and 1. So all I'm doing to the left side is either multiplying by a negative number or something that's less than 1, which is just going to make that left side smaller than it started with. So therefore, this inequality does work out. So therefore, we can say that the original series converges by the direct comparison test. Now, some people like the limit comparison test better. Some people like the direct comparison test better. For most functions where you can use, or series where you can use a comparison test, either one will work. But there are a few that only the limit comparison will work, and there are a few that only the direct comparison will work. So unfortunately, that doesn't allow you to just say, okay, I'm going to pick this one and always stick with it. You have to know both. If a trig, very good. If something involving trig is involved, you're going to have to use the direct comparison test because limits don't work very well with trig functions since they oscillate.
What is something that will not work with direct?
Sometimes it's just hard to get that direct comparison and get that inequality to work out. Okay, number 6, last one. Regardless of which method I use, which comparison method, I'm going to have to pick a comparison series. So what do you want to compare it to?
1 over 3 to the n.
Okay, 1 over 3 to the n. Or 1/3 to the n power, same thing, but it's a convergent geometric. Let's use the direct comparison just to reinforce that since we just did it. And then I'll actually work it using the limit comparison too. So for the direct comparison, since 1 over 3 to the n converges, I need for 1 over 2 plus 3 to the n to be smaller. Is that a true statement? If you're unsure whether that's a true statement, then cross multiply. So 3 to the n is less than or equal to 2 plus 3 to the n. You could even go so far as to subtract 3 to the n from both sides. 0 less than or equal to 2. Is that a true statement? Absolutely.
The denominator of the left will always be
right.
bigger. So
Or from this step right here, on the left side, your denominator is bigger, and a bigger denominator means a smaller fraction when the numerators are the same. Okay, so that I just proved converged by the direct comparison test. Or I could take the limit as n approaches infinity of my original one over the comparison. Which would be the limit as n approaches infinity of 3 to the n over 2 plus 3 to the n. Okay, I'm hearing 1 and I'm hearing 1/2.
it's just going to be 1 with 2.
Why would it be 1? Yeah, the 2 doesn't really matter when n is really, really, really big. And you can think of it in terms of basically the degree of the top and the degree of the bottom. That 3 to the n is the same. So the coefficients in front of 3 to the n are both 1s. So that limit equals 1. It's a positive finite number. So therefore, the series converges by, 3 to the n. It converges by the limit comparison test. It's interesting about which one people prefer. You prefer the limit or the direct? So whichever one you want to use, that's fine. If you are using the limit comparison test, I told you on Friday that when you were doing the integral test, that the value of that integral is going to get you a lot of points on that problem. If you're using the limit comparison test, I'm going to be looking to make sure that you get the right value of the limit right there.
So wait for the limit comparison test.